compartmentalize mathematics. That is very, very true. All right, so I want to describe this affine group. See, whenever you say describe a group, what does that mean? For example, last exercises we have described or Panoshi as trying to describe what is a dihedral group. That means in terms of the known group we are describing dihedral group. And what were the known groups? You saw there. Zm, the cyclic groups, and some action on the cyclic groups. That was used to describe the dihedral group. Same thing when you, for example, when you studied set theory and you wanted to compute or you wanted to define cardinalities, you chose the sets that you were comfortable with. For example, natural numbers or finite set 1 to n or rational numbers or real numbers or complex numbers. These models you wanted to compare with the arbitrary sets and then define something. So same philosophy. This we have a affine space E given, and we know we have defined this set of all affinities, and then we got this group, and that we call it a group of affine group of E, and this group is closely related to two things. See, philosophically, if you see what is E got out of, we got E out of the vector space addition. So vector space was given to you. For example, Rn. Suppose your vector space was Rn or k power n, finite dimensional case, then they were given to you. So therefore, this group has to something to do with those vector space additive groups and the linear maps which came out of that, because this F0 is a linear map. So therefore, and we are looking at the bijective maps because we are looking at the isomorphisms, automorphisms. Therefore, this group has to be related to the V plus and GLK, and that is what I am going to patch up together. So that is what one means by description of the affine group. And I also told you last time, pay attention to, I made that comment maybe in lecture 6. At the end I made that comment. Where is that? 7 maybe. Today is 8th lecture. Here. No, I forgot where it is. I said this group is different from, if I say the automorphism group of the V plus space, because that V plus, that will give you only the additive operation. But we are taking, now we are bringing in the linear part. So therefore these are different. Where is that?
Sir, after the definitions, affine isomorphism.
After where?
Definitions of affine isomorphism.
Which lecture?
6th, I think. 6th, yes, sir.
This is 6. This is 6. Oh, where is it? After the definition. Now here. Note the difference between this and this. This also makes sense, right? This is precisely we have described in earlier lecture. That is automorphism group of an. Actually, we have defined it for homogeneous spaces, and E is not affine includes homogeneous, and the action is simple. So this one, so this group is bigger than this, because this affine group will not only deal with the additive maps of V, but it will also deal with the linear map, because the affine affinities have linear part to be, F0 will be the linear part. See, F1, F0 is a K-linear map from V to V. So therefore it becomes more difficult because you have more constraint. All right. So, and what I say now, the earlier theorems which I noted, that I am briefly recalling it here. So that is a group of affinities of V. Affinity means affine automorphism of V. What does that mean? There is a linear part, and if you fix one point and everything you do with respect to that fixed point, it's not a fixed point, but the point is fixed, origin is fixed, then it is essentially the V. But V has a fixed origin that you cannot change. So if you are Rn in a vector space Rn, if you are doing something, some calculation, that 0 is fixed, that you cannot change. That is an additive identity. Whereas in E, you have a choice, and that choice should make life more easier. That is the philosophy. All right. So what is this natural map? This natural map is F. So first of all, this map, F going to F0. Makes sense? Because this F0 is well uniquely determined by this F. So this is indeed a map. Second thing I am saying, this map is surjective. That means what should I prove? Given any K automorphism of V, K linear automorphism of V, I should be able to define an affinity of E. But that is what I did it in this last part in this lecture. Where was that? 6. See here, I will show you. That is precisely what I was doing that. All right. Here, look at this theorem. If I have given F0 and given point P0 in E, E equal to F we are taking, and Q0 I will take what, and Q0 another point. Q0 is another point, and what does it say? Given F0, a linear map from V to W, then there exists a unique affine map F from E to E which maps P to Q, P0 to Q0, and F0 is a linear part of that. And we have also seen if F0 is bijective, F is bijective. So therefore that will be the affinity. So the existence is guaranteed by this theorem. So this theorem says that this map here is surjective in particular. And what is the kernel? Now these groups are multiplicative groups, multiplicatively written, that the composition is a structure there. So when it is surjective, that we have checked. And what is this group? This is the translation, group of translations of E. So there are as many as Y. If Y is given vector, then I can translate the points in E. And that gives me a bijective map. And then this map is, and these translations are also affine maps. That is also very clear. And what is the linear part of that? This identity. Because this Y is not disturbed. So that's I've written here. For every Y, linear part of Ty is identity. So therefore there is an injective map from here to here, Ty going to Ty. And where does it go further? The linear part, but linear part is identity. That means it is in the kernel. So therefore kernel of this map, image of this map is contained in the kernel. That clear? And converse also. So exactness of the above sequence now follows from the theorem on page 0611. That you should read it. And I said check this. And remember, every time for all of us actually, not only for me, for everybody, the next lecture will depend on the earlier lectures. So it is advisable the same day or next day morning till afternoon, you can read up, collect your difficulties and report your difficulties. We are there to help you. All right. So is it now clear that therefore this is a normal subgroup because it is a kernel of a group homomorphism, and therefore the quotient group makes sense, and the quotient group by first isomorphism theorem, it is isomorphic to the automorphism group of V. And probably when you studied linear algebra, you were not used to this language. This is only the language which I have not talked about bases, I have not talked about matrices and so on. Is that clear? So therefore, this affine group of E, what we want to describe, that is a quotient group, and the quotient group is known to us very well. And the normal subgroup is also known to us very well. It is isomorphic to V plus. And we want to use this information to describe this group. All right, so that will be done by the semi-direct product. All right, and these are the examples. And now I will start on this lecture. So now precisely now I will recall what is a semi-direct product. And actually the particular example you already know, that construction of dihedral group come under this. So dihedral group is a very particular case of this. All right, so what is it? First I will give you a motivation. So suppose G is a group given tree. And suppose it has subgroups N and H. These are two subgroups. And in general, when you take N times H, this is all, take all products. So that is, I want to use the same notation. So A, X, A in H, and X in N. When is this a subgroup? This is a subset of G, right? So is it always a subgroup?
So only when NH equals to HN.
Very good. Yeah, but what you are saying is too complicated to check. So can you tell me a little bit better answer? Your answer is correct. So this is a subgroup only when NH equal to HN. Very good. But how do you check this equality? Is there any better answer? Anybody knows better answer?
Equivalent to saying either N or H is normal in G.
N is normal in G. Then yes. So if N is normal in G and H is arbitrary. H arbitrary. Then it's easy to check this condition. Or easy to check directly that NH is a subgroup. Let me check once again. So we know the group G is operating on G by conjugation. Right? So G is operating on G by conjugation. So it is in fact operating, so G is operating on G by as a group of automorphism, because the image doesn't go only in S of G. This is action homomorphism. It actually lands inside the automorphism groups. Not only automorphism group, it lands inner automorphism. So this map is actually kappa. This map is actually kappa. Any G going to which automorphism? Kappa G. Kappa G is the inner one, which will map X to Gx G in X, isn't it? And we saw this is an action operation. So in this case, one says G operates on G by automorphisms. That is because the image goes inside the automorphism. That is just. And now if I restrict this homomorphism, this kappa is a group homomorphism. So if I restrict it to H, so H sit inside G, therefore I have a group homomorphism from H to automorphisms of G. Doesn't that mean that H operates on G by automorphisms? This is by restriction, right? Now if I, instead of, so what is this operation? So this also means that I will write here now. So H operates on H by automorphisms. Because H is normal given, so all conjugation will fix H, fix N. N will be mapped onto N. So the same H, same map will give us operation of H on N, and which will be by automorphisms. So this kappa G, when G is in H in particular, and if you take X in N, it will go inside N, and that will be an automorphism of N. So therefore, this condition H normally in G, that got translated into this. H operates on N by automorphisms. See, this adjective usually comes because they are not arbitrary permutation, but the permutation themselves are group homomorphisms. That is why this adjective. All right. Now, we have therefore a natural map now. Map is from where to where? N cross H to G. What is the map? Any X, comma A, this goes to X. And I say this map is bijective. First, let us check it is bijective. When is it bijective? The bijective, so the map is bijective, this map is bijective is equivalent to saying NH is H, NH is whole G. Because if NH is whole G, any element of G will be product in between. So any G will be then, any G will be of the form X times A for X in N and A in H. And therefore given a G, it will be this and it will come from this. So that means the map is surjective. Also the map is injective because if somebody goes to identity, so this equality is surjectivity of this map, surjectivity. Let us see what injectivity means. Injectivity means I say N intersection H is empty, not empty, it is only identity. Because suppose there are two, suppose XA and YB, they go to the same. So XA equal to YB, suppose this. Then what do? I want to conclude A equal to B and X equal to Y. What do? So can I leave it for you to check this? I want to leave something to check. This is a trivial thing to check. So I will say check. All right. So, but so therefore we got the condition. When is the whole group? So therefore this group H, G we have decomposed in two pieces: normal subgroup cross subgroup H. So if you wanted to study group G, we can study them separately. And then this is the direct product. This is the product operation. This is the product of groups, Cartesian product of groups, where these have nothing to do with the neighbors. They are not mixing. That is the operation. Component-wise operation. That is the direct product. Now I want to consider converse. That means given, so I want to look at the converse. So what should the converse be? Given two groups N and H, and I want to construct a new group G, so that this N is normal there and this H is a subgroup there. So I want also to this sit inside this and not arbitrary group wise normal. That means there should be a homomorphism, injective homomorphism of group N into G, so that the image is a normal subgroup, and here there is a injective homomorphism. These are group homomorphism. I am looking for this. So I am going to decompose the group G in such a way that G will look like N cross H. Look like this, but this may not be the structure of the group that I have to arrange. This N becomes normal here and it becomes a subgroup here. That is the problem. And precisely when I do this, that construction is called a semi-direct product of N and H. So that is called a semi-direct. So I have to define now, I have to give you condition when it is possible. So that is, if you want, I am defining what is a semi-direct product of two groups. So obviously I will need a condition, and that condition who will dictate? This earlier case will tell me what to do. That is, this experience, what we got from this example, that should tell us what to do. It will not be as simple as this, but it will not be difficult either. So what are the assumptions now I am making? So assumptions I am making are the following. And whatever assumptions I make, those assumptions should be satisfied in this original case. Then only it is called a generalization of the known case. All right, so what is the assumption? All right, so the assumptions are the following. H is a group. Operating on the group. So N and H are given groups. They are given to you. And their structure, their group structure, nothing to do with each other, sets have nothing to do with each other, and so on. That is understood. So these are arbitrary groups. And in addition to this, I am assuming this. H is a group operating on N by automorphisms. And what does this mean? The action homomorphism theta should be a map from the group H to the group automorphism group of N. Is that clear? That is the meaning of it is operating by automorphisms. That means the elements of H, if H is an element, I don't want to call it H. If A is an element, because if A is an element, then you have this bijective map theta A. This is N to N. This is not only bijective, but it is a group homomorphism also. This is extra. That is where we say it operates by group automorphisms. So that means theta suffix a evaluated at 2 x and y, that is same thing as theta ax times theta ay. It respects the group operation here. The group operation here is also written by the product operation. Here is also written by the product operation. Are the assumptions clear, Sonakshi? Sonakshi,
Yes, sir.
assumptions are clear?
Yes, sir.
All right. Then I am going to define a new group G. Then we want to define G. And G, the set, I will take n cross H. Product. This is the Cartesian product. Of sets n and h. That means the elements of G are pairs, x comma a, where x is in n and a is in h. That clear? All right. Now I want to define the group structure here. So that means I should tell you how do I multiply in G. That will give you a binary operation. X times A times Y comma B. This is what I want to define. So I here define this. How do I define? So what do I need? I need a pair. The second component is in H and the first component is in N. And they have to do with something with these 4 elements, no? So the second component is AB. This AB is the operation in H. This is I multiplied them in H, which were given to us. And the first component is this X at X. In the product case, we have to multiply by Y. But I don't multiply X by Y, but I multiply X, the first one, and I take theta of A, that is a map from N to N, I take the image of Y. So let me write it clearly. So X times theta A of Y. So this is indeed an element in N cross H by our given assumptions. That clear? So I made a definition. And with this definition, I will now check to you that G is a group. And we have a natural map from N to G, the natural inclusion. So what is the map from N to G? This is our G. As sets, it is G. G is this N cross H only as sets. And there is a natural map here. What is the map? Any X. The natural map is X goes to X, comma identity in H. So EH. And also from N to G also I have a natural map. Not N to G, H to G. H to G is also natural map. Namely any A going to identity in N, comma A. And I have to do several things to check now. One, G is a group under this operation. That means G has identity, it is associative, and every element has an inverse. This I have to check. Then another thing I have to check is these maps with this group structure, these maps are group homomorphisms. The third thing I want to check that this N becomes a normal subgroup. All these things if I check, we are done. That means I have constructed a group G in which now that n became normal, and so on. And some more properties we will check. All right, so one by one we should check. So to say that it is a group, so with this operation, with the above binary operation, G is a group. That is what we are checking. So I have to check first what is the identity element. So can somebody tell me what is the identity element? Yes. Who can I tell? Roshini, can you tell me what is the guess for your identity element?
Yes, sir. Identity element will be the pair.
I can't hear you.
Hello, sir.
Yes.
Yes, the identity element will be E suffix N, E suffix H.
So she says En, EH. This is the identity element. In G. Is that clear? It is clear because see, if I take XA times identity, no, then I have to, if I multiply any XA by this, what happens? X and the theta A is also identity. Anyway, this at Y is also, this Y is also identity. So, and theta is a group homomorphism, and therefore identity here will go to identity map here, and so on. So it is, this is just a simple checking. So I will not check this. But remember what you have to check. You have to check that XA times EH, EN, equal to XA. And also you have to check the other way. This is also EN, XA. And you close your eyes and look at the definition and look at what is given. The theta is a group homomorphism. And this is an action. So this is also group homomorphism. All that you will need to check both this equality, which I am leaving it to you. The next thing what I have to guess, what is the inverse? Associative also you have to check. Associativity. This is also very simple, so I will not check this. Now, more importantly, we have to check the inverse. So what is the inverse of x comma a? Any guess? At least second component, you can guess. Second component, you need identity. So second component is nothing that you need identity here in H. So this will be A inverse here, the second component. And the first component? Oh, Ahmad Bhatt, you were the one who spoke something. Do you have a guess? What is the first component? I already said last time also, I don't like monologues. So who can answer? Who can I ask? I am only asking guess. Guess may be wrong, but at least you should guess. Hello, Anupama. Are you there? Hello, Anupama. Not responding. This is the same problem. Hello, Himamshu. Himamshu. Who? Angel. Are you there?
So is it X inverse by any chance?
Who is talking?
Sir, Soham.
Soham.
Yes, sir.
Soham, where are you from?
Sir, I am from Pune University. I finished my master's.
So what is the guess for the first coordinate?
X inverse by any chance?
X inverse?
Yeah.
But you see, when you multiply, did you understand this definition?
Yes, sir. Yes, sir.
So when you take x inverse, the theta map also has to come in, no? See here, this definition.
Yes, sir. Yes, sir.
Theta map also has to come in. They are
Right.
not just product multiplication. I already said this multiplication is not product multiplication. We are using this on this Cartesian product of set. We are using the theta map to define the new binary operation, and that is what we are talking about.
Right.
Hello, sir.
Rahul. Tell me, Rahul.
Is it pi A inverse of x?
What?
Pi A inverse of x.
5?
A inverse of x.
A inverse of?
That pi A inverse. Pi
Theta,
suffix.
you mean? Theta.
Yeah, theta. Theta.
So, theta suffix A inverse
Of x.
evaluated
At x.
x or x inverse. Let us fix it. So, what do you want this? That means if I multiply this side, theta A inverse, let us say if you are saying x, A inverse, and if I multiply this by xa, what should I get? I should get identity on n and identity on h. I should get this. This is no problem. Here, what is the definition of this? This definition is what? X times theta suffix of this, that is a, and evaluated here. That is theta inverse, theta suffix a inverse x. If you have said x, then what is this? This is x times theta a compose theta a inverse evaluated on x. This is identity, so this will be x squared. But you need identity, isn't it?
Yeah. Got
This
it.
is wrong.
Yeah.
This is wrong. And now check this. So what will it be? What will you have to check? Now see, that problem will get resolved because instead of x, you are writing x inverse.
Yes.
And now this is identity, and identity evaluated on x inverse is x inverse. So the result will be x times x inverse, which will be indeed identity in n. So this will get cleared. Very, very simple. So therefore, what we have checked is, we have checked that every element has an inverse. And of course, I have checked only one way. You have to check the other way also. All right. So I am leaving it for you to check the other. So this, to check this inverse, you will have to check two equations. What are the equations? You will have to check that x times a times theta a inverse x inverse at comma a inverse. This is en cross en comma eh, and this is also equal to the other way, theta a inverse x inverse a inverse times x. This is also we need to check. Both these things you need to check. Then only it will be a group. Is that clear? So we have checked that G is a group. As I said, it is just a product set. But the group structure is different. The binary operation is different. So to distinguish that, so we should denote. We denote this group by n and not the cross product. Not this. This is obviously not allowed. So I will just change this notation to this. I'm just putting this cross product and then putting a line here. That is this. And this is called, this group denoted by this and is called the semi-direct product of n and h with respect to theta. See, theta plays very important role, and theta is a action of h on n by automorphisms. And therefore, actually, some people will also write theta here, just to remember what is that action. But if your action is fixed, in order to have cleaner notation, you just drop that in the notation, but you have to remember that is also playing an important role in the group structure of G. And now what we have to check? We have to check that. So there are natural maps now. N to this, there is a natural map, namely any x goes to x comma identity. As I said, they are only the product, Cartesian product. So this makes sense. And I want to check now. This is a group homomorphism for the given group structure here and for the new group structure here. So if you call this, what should I call it? Let us call it F. I am checking F is a group homomorphism. That means I have to check F of x times y equal to fx times fy for all x, y in n. But what is f of xy? Can you tell me? This is xy identity in H. What is here? This I know what it is. This is xEH and this is YEH. And what is this product? We are taking in this group. So what is it? Can you tell me? The second component is no problem, EH. And second, the first component, X evaluated here, the theta suffix will be this. So X times theta of EH inverse and evaluated at Y. So you have to know what is theta EH inverse. But what is theta? Theta EH is what? Because theta is a group homomorphism, identity here should go to identity here. See, this is a group homomorphism. So identity here should go to identity here. So that is, this is N. No, this is correct. So this theta H should is identity map on N. So therefore, theta inverse is also identity. Theta, not inverse, theta inverse of this is precisely theta EH inverse. And therefore, this will be just Y. This will be just Y. And therefore, XYEH. And this is also XYEH. So done.
Hello, sir.
Yes.
So why you are taking theta E inverse H? We defined theta A.
What is the map?
Theta AY.
What is the operation? Where is the operation? Oh, theta. A. So I have not taken. I should not take inverse.
Okay.
Sorry, I should. This is only the this.
EH. Yes, sir. Okay, sir.
So I don't need even this. Good. Who was that?
Rohitesh Pradhan.
Where are you from?
Sir, South Bihar Central University.
Okay, very good. So thank you very much. So therefore we checked it is a group homomorphism. Next thing I want to check that it is a normal subgroup. So we have to check that the image of Fn here, n is a normal subgroup, or it is maybe better to check that from G is this group, and here I just take the second projection. That means any x comma a, that is going to A. And I should check it is a group homomorphism, and I should check the kernel is N. If I do that, that will prove that the image of N is a normal subgroup there, and we will be done. So this is easier because it is always better to check normal subgroups are precisely the kernels of the group homomorphisms. So first, is it a group homomorphism? So see, the group structure is, it is not bothering the second component. Second component is very good. So if I take two elements XA and YB, where does it go under this projection? It goes to AB, which is also this A is the image of, if you call this name as G of XA, and this B is G of XB, YB, and this is whatever it is. So this is the other AB is G of somebody, no? So it's G of this. We don't need to multiply for this purpose. Even if you do multiply, what is it? It is x theta x times theta A evaluated at y comma AB. So what will be G? G of this map, G of this element is precisely this, because it is second group. Therefore, what it checked, that G is a group homomorphism, this is checked. And what is the kernel? Kernel is whoever goes to identity there. So that means kernel of the G is precisely all those elements x comma a, such that G of x comma a is identity in H, but this is precisely A by definition. So A is identity in H, therefore this kernel is precisely x comma EH, and X is there in N. So this is obviously the image of N under this F. So this is image of S. So therefore, and F is injective is also clear. Did we check? F is also injective. That also you need to check. So I will leave it for you to check F is injective. That is only set theory. Where do X go? To E comma H. And if some other Y go to Y comma EH. And these two elements are equal. But the set is N cross H. So the pairs are equal means each component is equal. Therefore X equal to Y. Therefore it is map is injective. So I checked it orally only. All right. So we have checked that. What did we check? Let me summarize. What we have checked is N is normal in this and semi-direct product H. When you say N, that means the image of N. That means we are identifying N with its image. And also we have checked that G is, what is G? G is, as I said, it is N cross H. So that means we have decomposed this group G in two pieces, N and H. The first part is normal and the other part is so that has generalized this above construction of this product. All right. Now let us go on. We should have example, at least one example of this kind. All right. So examples are very important. Examples. Let G be any group. And look at the automorphism group also. This is the automorphism group of G. So the elements of this group are precisely the automorphism. Phi, such that phi is a map from G to G. It's a bijective map and group homomorphism. And this is a group under composition. In fact, it is a subgroup of S of G. So this is a group under composition. And that we call it automorphism group. And in every subject we consider automorphisms. So we have seen automorphisms in the topology are continuous homeomorphisms. Homeomorphisms are the bijective maps which are continuous, and inverse is also bijective, continuous. In a group case, we don't have to check the inverse is a group homomorphism, it is automatic. In a vector space case, they are linear maps which are bijective, and in this case also you check easily that the inverse is also linear. So inverse you don't have to check. In some cases we don't have to check the inverse is also that structure preserved. But in topology we do have to check. And this automorphism gives us a lot of room to play. If there are no automorphisms, then we have no room to play. For example, so what should be automorphism group of a ring? What are rings? So R is a ring, and for us, a ring means always a commutative. R commutative. And R has identity element. R has one is multiplicative identity in R. And what should automorphism group of the ring R mean? That means they are bijective maps, they are ring homomorphisms, they should carry 1 to 1, and the inverse also should have this property. Inverse also should be ring homomorphism. And for us, ring homomorphisms should carry always 1 in the ring to the 1 in the other ring, wherever you are defining ring. Is that clear? These are automorphism groups. So can somebody tell me what is an automorphism group of the ring Z? How many elements this has? Hello, Nikhil. Nikhil Bharti. Nilesh.
Yes, sir. Z2. Z2.
Z2. Which are the automorphisms?
Identity and minus identity. Oh, isomorphic to Z2.
But I just now said ring homomorphism should require identity should go to identity. So is minus identity means where? Where will one go? Where will one go? Tell me your definition.
One should go to 1.
One should go to 1. And then where will n go?
N goes to n. It's unique.
N goes to
N.
N. So this map is identity map only.
Yeah.
So there is only one ring automorphism from Z to Z, namely the identity map of Z.
Yes.
So there is only one.
Yeah.
Now can you tell me automorphisms of the group Z mod P under addition? This is automorphisms of the group.
Sure.
Yes, please. Please think about it. So computing automorphism group is a very important issue because we want to know how many automorphisms are there. And the automorphisms are called the symmetries of that object. So we want to know how many symmetries are there. That is the topic I will take also in a larger scale in the coming lectures. All right. So we have constructed this group, and now I just want to make you sensitize that what was the dihedral group. Okay. No, I have not yet finished here. The example G is a group and automorphism odd G is an automorphism group of G. Then I say the following important remark. Then odd G operates on G by automorphisms. So to justify this, why should I give you? I should give you a map theta, the action homomorphism, and it should be from where? From automorphism group, because automorphism group operates. And to where? It is operates on G, so it's the map should be inside a G, but it operates by automorphism. So actually the map image should be inside the automorphisms of G. And what map? Identity map. Very natural action. So this is a very canonical operation, canonical action of odd G on G. If you want to write in the other form, that means you need operation map, that means odd G cross G. You want a map to G. And what map? If you have a sigma automorphism, G is an element here, then what can you do? You evaluate sigma edge. It is so natural. And this is operation map. You have to check that it satisfies those 1 and 2 properties of the operation. And we know that to give an operation map is equivalent to giving a theta. So this automorphism group operates on G by automorphisms. Therefore, I can definitely talk about this is my who is operating, odd G is operating. So that is my H and the G is my N. And then I construct a semi-direct product. So that means I construct G, the semi-direct product odd G. And this group is very, very important. It is, I am denoting it by a whole G. This is called holomorph of G. And then, now we come back to our problem from the last lecture. What was our problem? Another example is, if you take vector space V and K-linear automorphisms of V, that group also operates on V by automorphisms. Therefore, I can take semi-direct product. That is the construction. And this semi-direct product is precisely what I want to prove, the affine group of V. And that is what the example we saw it from here. Right? So therefore, what is the conclusion here? AE is isomorphic to semi-direct product of what is V now? V that underlying V. V that is T. V you are identifying with translations. And then the semi-direct product with GL. K. This is what we want to prove. That means we want to give a map, and actually the maps are there. You just have to check the multiplication here is same as multiplication here. So that we will do it now. Already I exceeded the time. so that we will do it in maybe next lecture or tutorials, and please go through these lectures so that you have no trouble in understanding. The material is getting accumulated, so I request all of you to go home and read it, collect your difficulties. Next opportunity you ask them, we are there to help you. But please respond. You are already, we saw there is so much drop in the participation. All right, so